My full-time job is to write software or to take software that other people have written and improve it somehow. So I improve scalability or I improve capability of scientific software. I do something to make the code run faster or better in some way. And the process of transforming a code in that way to improve it is what I call performance engineering. So that's what I'm going to present today, tell you about this process and one of the tools you can use to do performance engineering. But first I wanted to show you some late breaking news. I got this email from a client about 45 minutes ago, and it was just too good not to share with you guys. This is the results of some performance engineering I was doing last week, working with some folks who are running one of the largest CFD simulations ever executed. It's about 1.5 billion nodes running on the 15th fastest supercomputer in the world. And these guys have been working on their code for several decades now. They get excited about speedups of 1 to 2%. Last week, I used performance engineering, and I used the tools I'm going to show you, Tau and Tau Commander. I was able to find 2 lines of code. And by changing those 2 lines of code, I got a 33% speedup in their code, which is pretty serious money when you start to run a large supercomputer for any length of time. So these guys are very happy about it. My point here is I'm not presenting theory or abstract feel-good thoughts. This is real stuff. And if you try to use this process on your code, I think you will actually get some serious speed up out of your code as well. So first, I wanted to start with a silly introduction. I wanted to compare Mira to an abacus. So an abacus is just a couple of sticks with beads on, and you can use it to do basic math. And a human with an abacus can manage about 8 flops. If you're really, really good, you could do about 8 flops on an abacus. That gives you, given the average human metabolism, it gives you about 1 flop for every 10 watts. So that's not really great, which is why we use supercomputers, right? At 10 petaflops, Mira is equivalent to about 1.25 quadrillion abacuses. Or, put it another way, if you give every living person 172,000 abacuses and get them all to run them simultaneously, we can get rid of Mira. We don't need it anymore. We can just use abacus-based supercomputer technology and call it quits here. The problem with this approach is it's not very scalable because this thing is even faster. This is Aurora. Aurora is going to follow on to Mira pretty soon. It's 18 times faster. 18 times faster than Mira. Close to 3 times as power efficient. So this machine is enormously complex. It's on a scale that just boggles the mind. A human mind can't deal with the idea of 22.5 quadrillion abacuses moving in step to achieve anything. You're going to have to use performance analysis tools to get any kind of good performance out of this thing. If you don't use performance analysis tools, this is going to be you. You're going to be able to see your performance frozen deep inside of the machine, but you're not going to be able to get at it. Right? You're going to be stuck here just staring into the camera saying, seriously? Because I have this amazing resource, I have Aurora, and I know that it should be running a lot faster, but I can't seem to get the performance out of it. Gone are the days when you could just be a brilliant programmer and through the sheer power of your genius create a software code that would do what you needed to do on the machines. The machines are too complicated to do that anymore. If you use performance analysis tools like Tau, HPC Toolkit, Vampire, vTune, whatever, you can get real performance out of your code. And finally, unfreeze your science fish and get the delicious science that you need. All right, that's the end of the silliness. That's no more silliness. I'm going to get serious now and actually talk about the things I came here to talk about. Performance engineering. What is performance engineering? Performance engineering is just a process. The tool is almost irrelevant. The idea is think about what you're trying to achieve in your software, ask yourself a couple of questions, and then go forward to find the bottleneck or the piece of hardware, whatever it is that will enable you to solve the problem. So take a moment and go through this with me and think about your application. Think about the code that you're writing or you're using and try to answer these questions in your mind. The 3 questions you should think about when you start the process of performance engineering are, first, what is my target? A target is a combination of hardware and software that completely encapsulates the running environment of your code. So, for example, are we dealing with a shared memory system that uses OpenMP, or maybe CUDA? Is it a distributed memory system that uses MPI? Does it use both? What kind of compilers am I using? Are Intel compilers, PGI compilers? Are there external libraries that I should be aware of? This all goes into your target. And this is an abstract idea, right? I'm not talking about something you're going to type into a computer. This is something you should get right into your mind. Thinking about what is your target. And then what is your application? What does the application actually need from the target system? Does it use MPI? Does it use CUDA? Does it use OpenMP? Does it use OpenACC? Do I think the application is going to be compute intense? Do I think it's going to be data intense? Do I think it's I/O intense? Try to answer these questions for yourself before you go charging into the tool, and the data that comes out of the tool will make a lot more sense. And the final question you should ask yourself is, what am I trying to measure? Now, for example, if I have an application that's compute intense, I probably want to measure things like flops. I would like to know if I'm getting good floating point efficiency out of a machine that is computing intense. But if I'm working on some sort of graph problem that is definitely not compute intense, then flops are irrelevant, so don't measure them. Instead, measure something like maybe cache misses or even file I/O throughput. So think about what it is you need to measure. And then think about how are you going to measure it. We've already seen some examples of you can use indirect measurement through sampling or direct measurement through probes. I'll go into that a little more, but it's been covered already. And each measurement approach has its own advantages. So think about what is it I want to measure and how I'm going to measure it. Those are the three questions. What is my target? What is my application? What is my measurement? If you can answer those questions, it allows you to build workflows for performance engineering. If you can take one target, one application, one measurement, you combine them together, it's an experiment. The experiment fully describes the running environment of your code. And what is this good for? Well, we heard a lot about Provenance the day before. That's one thing that this is really good for. If I can define my target, my application, my measurement, combine them into an experiment, then I have the complete provenance for my performance analysis. It also allows you to iterate over different combinations of these abstract objects and think of different ways to answer relevant questions. For example, you could say, what platform is best for my application? Now, many of you probably already have access to multiple supercomputers with very different performance characteristics. And if you don't, you certainly will by the time, in just a few years. It's very common to be able to use, to have a supercomputer that either uses GPUs or maybe it uses Xeon Phi. So think about holding your measurement constant, your application constant, and varying your target configuration. And then each time you select a different target application measurement, it creates a new experiment, right? So you can kind of see where this is going. You can create workflows. You can create an abstract model for performance engineering. And I haven't even discussed about tools yet. This is just a way of thinking about getting the performance out of your system. Now, I am going to stop here and say that there is a tool, which I'm going to present, called Tau Commander, that makes these objects first-class entities. You can actually define a target, an application, and a measurement in the tool, and it will set up your experiments and maintain the provenance for you and do all that stuff for you. But most of my time today, I just want to introduce this concept to you before I get into the details of the tool. The next thing you can look at is, what are the performance characteristics of my application? This is what most people want to know. If I hold my target and my application constant, if I say I'm running on Mira, I'm going to run my code, what are the different measurements I should take to find out how well my code performs on Mira? Or how well does my target perform various tasks? This would be relevant to benchmarking or purchasing efforts, right? You have to figure out which computer should I be using for a wide workload. Well, hold your measurement, your target constant, and vary the applications. So this tool, Tau Commander, this is installed on Mira and Vesta and Cetus. You can try it out, and if you're interested, I'd love to show it to you in the hands-on, but I want to caution you and say that this is an alpha release of the tool. We've been developing this thing for about 2 years. I've been using it internally for about a year now, so it's relatively stable. But early adopters only. If you feel like trying to approach this performance engineering workflow with a tool that might or might not help you, then let's look at it in the hands-on session. I'm not going to talk too much about this tool today because it's a lot easier to learn through using it. I'm going to talk about the tool that sits under Tau Commander. Tau Commander takes these targets, application measurements, takes these high-level concepts, and feeds them into a thing called the Tau Performance System, which sits underneath Tau Commander and actually does the job of getting the performance data and turning it into an actionable result for you. The Tau performance system has been developed for about over 20 years now. It's a project out of University of Oregon, and there's a large community of people who contribute code to this. We work with folks like the Scorpio developers and Vampire developers and independent performance analysts to constantly improve Tau. Tau is hosted at University of Oregon, but I'm not at University of Oregon, but I'm one of the Tau developers. And it's open source BSD license, so you can take this thing, you could build new things on top of it and not have to worry about licensing issues. And one thing to understand about Tau is that it is not an integrated tool. Like HPC Toolkit, it has a very nice sort of integrated feel to it. You feel like you're using one tool when you use HPC Toolkit. With Tau, you don't get that feeling. Every piece of Tau was written by a different person at a different time for different reasons, and it has different command line arguments and different configuration files. So it's this sort of diverse set of different tools that you cobble together to achieve a result. And that's why this idea of thinking about target application measurement and building your workflow and deciding what your end result should be, that's why this is important. Once you've defined that in your mind, it's a lot easier to pick up these different pieces of Tau and glue them together in the right way to get the result that you need. A good thing about Tau is it supports every HPC platform by definition. We have a good relationship with all the HPC vendors and get early access to HPC hardware. So the moment this stuff hits the ground, Tau is usually installed on it. So this creates a very nice apples-to-apples comparison across a great number of high-performance computing platforms. If you want to see how does your code stack up when it's running with CUDA versus when it's running with, maybe on the Xeon Phi, and you take profiles from NVIDIA Insight and you take profiles from Intel vTune, guess what? Those vendor tools are each going to say that their vendor platform is the best one. And there's actually disclaimers attached to these tools that say, if you use an Intel vTune on Xeon Phi, it's going to tell you that Xeon Phi is the greatest thing ever. So if you want a fair comparison of platforms, you need a third unbiased platform like Tau that can level the playing field and give you a fair comparison of the two platforms. Tau also supports a diversity of measurement approaches. So you can use profiles or you can use traces. Now these are technical terms with very clear definitions. When I say profiling, I mean a file that contains summary statistics. There is no timeline data in a profile. I can see how long the code spent in any code region. I can see when messages were sent or received or how many messages were received, but I can't see the order of events. I can't see if time was lost in a particular collective operation. Normally, this is not a problem, and the trade-off for this is that profiles are small. Usually, a profile is on the order of kilobytes or megabytes. If you run this I ran this a few days ago on 14,400 cores of a Cray, and the profile was about 60 megabytes after running for an hour or so. So profiles have very little impact on your runtime. Traces have all the information of a profile, but they include a timeline. Every time there's an event, the timestamp is attached to that event. And this means that traces are enormous. They are many terabytes, frequently many terabytes. And you will need tools like Vampire that can cope with enormous amounts of data to deal with a trace. That also can have a very heavy impact on your runtime if you're not careful. So you have to think, do I need a trace? Do I really need to know the order of the events in my code? Maybe I only need to know the order of the events in code in a certain part. I don't need to know the whole thing. I just need a certain part. Maybe I should use a profile to figure out what that certain part is and then use a trace. Tau can do both of these, so you don't have to learn two different kinds of tools. Now within profiles, you have a couple of different kinds of profiles. You can have a flat profile. This will just show you the data. You can have a call path profile, which is my favorite kind. This shows for every event. Think of a function called foo, and foo is called from maybe two different call paths. Your call path profile will actually show 3 timers for foo. You'll see one, which is the sum of time spent on all call paths leading to that event, and then you'll see one for every call path that led to the event. And this this is really useful for things like, say, MPI all-to-all. I want to be able to separate the cost of different calls to MPI all-to-all. So I don't just see that MPI all-to-all was expensive and then realize that that was because all of it was in this one initialization routine that I don't really care about. So using a call path profile can separate the cost of different events in your code. And then finally, phase profiles. This is more of a logical way to divide your profiles. If you have a code, and many codes do this, they start with like an initialization phase, maybe they do a transport phase, then they do a chemistry phase, and they do a finalization phase. You can define those phases and then get a different set of profiles for each phase. And that's a good way to separate the cost of events by phase, logically by phase within your code. So it comes down to how much data do you want? Now, how much data do you really need? The red text here, these are the defaults. If you use tau and you say, tau, give me a profile, you're going to get a flat profile. It'll be a few kilobytes large, pretty much no matter how many cores you use. Or if you say, tau, give me a trace, it's going to be many terabytes. So just be aware of what kind of data you need. Tau can also do either direct measurement with probes or indirect measurement with sampling. We've talked about this a little bit. Probes means tau will take your code and it will change your code. It will actually go and insert code into your source code that invokes timers around certain regions. Normally, this is not a problem. Now, if you're not careful about where tau is putting those timers, the overhead can be significant. So you should be aware of it. But the advantage to this is that your measurement is going to be exact. If I have a timer starting when I enter a loop and stopping when I exit the loop, I know exactly how much time was spent in that loop or that function or whatever it is I'm trying to measure. If I'm using sampling, the sampling period means that I'm not going to get a complete picture of how much time was spent in that region. I can get a really good approximation, but it won't be perfect. Also, there are certain methods or certain events that sampling simply cannot observe. For example, you can't see when memory is allocated using sampling alone. You can't see when threads are created using sampling alone. You have to use a combination of direct measurement and indirect measurement to see the complete picture. So which measurement method do you want to use? That's another good question you need to ask yourself. When you're defining your measurement in your mind, this is when you should be answering that question. Do I really need to know exactly how much time was spent in every routine, or can I just use a nice statistical picture based on an indirect measurement, which has very low overhead? Tau works with a really sophisticated package of source code parsers that will insert these hooks into your code for you. Now, if you want, you can go in your code and you can add call tau start, call tau stop anywhere you like. But that's really not a great way to profile something with 2 billion lines of code. So use Tau's compiler wrapper scripts. In this way, take whatever your compiler is normally, for example, MPI-CXX, and just replace it with tau_cxx.sh. And that script will take your code, parse the code, insert the calls, and then pass it back to the original compiler, compile it, and you get an instrumented object. So that's a really easy and fast way to get very, very accurate profiles using Tau. Just change your compilers. So finally, when you're using Tau, you start by adding those hooks into your code. You run your code, that's your measurement. And then that gives you data. And then you use analysis tools that are bundled with Tau to take a look at what the data actually means. And like the tools we've seen already, Tau can't tell you, in plain English, your code is slow because you have a load imbalance in function bar. It can only show you the data, and you have to derive that information by looking at the analysis. So to get that information, start with instrumentation. Add probes to your code, wrap external libraries, whatever it is you need to do. Use the Tau compiler wrapper scripts, and I'm gonna show you concretely, how to do this, and we can go over this in the hands-on as well. But I don't want to get too lost in the details because it will be here all day. Once you've added the hooks into your code, or you figured out that you want to use measurement via sampling and you don't want any hooks, run your code and you'll get your data. That's all it does, right? You just run your code, you get your data. And then finally, feed the data back into an analysis program like ParaProf or PerfExplorer or Vampire, and you get nice visualizations of what's going on in the system when your code was running. And now that should be enough for you to start to notice patterns in there. There are even statistical toolkits that are bundled with Tau that can do correlations and say, I noticed that whenever you have a really long time in this routine, this other routine has a really short time, something like that. So this is the part where I'm going to start getting into the details. This is where we're going to get a little deeper. I'm still not going to go all the way down to step by step, because let's do that in the hands-on. It's going to make a lot more sense if we can work together to do the step-by-step parts. But the key thing to know when you use Tau is that you have to set your Tau makefile. This is a Tau-specific thing. This is an implementation detail of the Tau performance system. It has no, there's no higher meaning to this. This is just an environment variable you have to set when you use Tau. Now, if you're on any of the BlueJeans at Argonne, there's a module called Tau Latest, software environment module. If you do soft add Tau Latest, you're going to get an environment variable called Tau, just $Tau. And that will point you at these various makefiles you can use. Now, each Tau makefile corresponds to a unique configuration of the Tau performance system. And it is up to you, the user, to match that configuration with your combination of the target and the application that you're using. So if I'm on, say, Mira, and I want to use BlueJeanQ timers to do my measurement, and my code uses MPI, and I want to do source-based instrumentation, then I'm going to use the red makefile. Now, unfortunately, I know that because I use Tau all the time, but there's no way for you to just look at this list and say, oh, that's the one I need. So you're just going to have to try a few and kind of work it out. Work with me on the hands-on, and I'll show you exactly what each one of these tags means. Some of them are pretty obvious, right? If you look at the bottom makefile, okay, so we're probably using GNU compilers. We're going to use BlueJeanQ timers to do the measurement. PAPI, I don't know what that means, but I'll tell you it means hardware performance counters. MPI, okay, that's obvious. pthreads, well, I guess my code uses pthreads. And then PDT means source-based instrumentation. So it's not as hard as it looks, but this is the biggest stumbling block, I think, for most new Tau users, picking the right Tau makefile. You've got to get it right. Your code might segfault, you might get weird data. You have to get the right one. That's another reason to use Tau Commander. It picks the makefile for you. I'll talk about that later. This summarizes, this is the one slide that shows you how to use Tau on Mira, Cetus, or Vesta. Do soft add Tau latest, set your makefile, change your compiler from MPI, XLF90, whatever, to the corresponding Tau compiler wrapper script. And then build your code and run your code. You can set additional Tau environment variables like I've done here. I've set some metrics, additional metrics, but you don't have to unless you really want to. And then finally use ParaProf, PerfExplorer, pprof, one of the bundled visualization tools to analyze the data that comes out. This one slide covers it all. Say it again, we've got the hands-on. If you'd like to prep a little bit for the hands-on, there's a workshop tarball at this path. The path is here in the slides. And if you unpack that in your home directory and just take a look at the README, you're off to a good start. Lots of examples in there that you can use to get started with Tau. So I'm going to skip ahead a little bit. I'm going to do like the TV cooking shows where they pull the pie out from under the counter. I'm going to show you what it looks like once you've instrumented your code and you finally got data that makes sense and you want to analyze it. What am I going to do? I know my code's slow. That's why I'm here. Tell me why my code is slow. So the first thing we can do is if you open ParaProf and you click on the label of one of these nodes, like click on the mean or node 10 or whatever it might be, you get this bar chart. And what I see in this bar chart is up in the corner there, the metric is time. I'm measuring wall clock time. The value is exclusive. What does that mean? Well, exclusive time is different from inclusive time. There's only inclusive or exclusive. Exclusive time means time spent in a code region and none of the code regions that it called. So think about like your main routine. The exclusive time of main will tend to be very low because main typically starts up and then immediately kicks off to some working functions. So the exclusive time of main does not include the time spent in other functions outside of main. Inclusive time means the time spent in a code region and all the code regions that it called. So the inclusive time of main will be the time of your application run. It should be, right? If it's not, then there's a problem somewhere. Yet the inclusive time of your code is the same as the inclusive time of main is the same as the runtime of your code. So I can see from this bar chart that all-to-all is taking a long time. Then there's this thing called dubwise MPI, which is actually the name of the application. And then there are a few FFT routines that seem to be taking a lot of time as well. So those are some places that I can focus on optimization. Not because they're taking a lot of time, that doesn't mean they're performing poorly. It just means that if I do an optimization in this region, the payoff will be significant. Don't optimize in code regions where no time is spent, right? Optimize where most of the time is spent. So the next thing I can look at is how many instructions per code region. So my metric has changed to PAPI FP ints, which is floating point instructions. I've measured floating point instructions, and I can see that this FFT routine is spending, doing a lot of floating point instructions. The number one code region that we saw in the previous chart, MPI all-to-all, it's not even shown, which makes sense, right? If MPI all-to-all was doing a lot of floating point, you'd wonder what is going on. That makes no sense at all. So this makes perfect sense. My FFT is expensive, my communication is not. How about cache misses? Well, I can change the metric to be L1 DCM, which is level 1 data cache misses. Now again, I see that my FFT has got quite a lot of cache misses. That might not be so good, especially depending on the size of the FFT and the size of my cache. Maybe this thing should fit into cache. So that is definitely a red flag. But MPI all-to-all is now the second highest cache miss in this chart. This is not a problem, right? Think about the nature of all-to-all. Every machine, every rank is sending a different message to every other rank. Of course, it's not going to use the cache well. So the fact that this is high on the bar, or high on the list, that's not a cause for concern. That's a sanity check. So this is telling me from these three charts, I should probably be looking at my FFT routine and try to optimize the cache use in there. Another thing I can look at is how much memory does the code use. This is really relevant for low memory machines like BlueJean, where you have actually a very small amount of memory per core. You need to know the footprint of your code. Total amount of memory allocated or deallocated. And exactly where is this memory allocated or deallocated? One thing I want to point out about this chart, this is not from a BlueJean, this is from a regular x86, but this was running a mixed language application. This was this code had a high-level Python wrapper calling compiled objects written in both Fortran and C, but then the C code had C++ wrapped around it. Tau can traverse the language barrier. It can go and show you the call path, going from Python down to Fortran, down to C through C++, whatever. And it can actually track memory allocations across these languages. If memory is allocated in your Fortran object and then used in your C++ object, Tau can track that. That's very useful for debugging and trying to figure out why row major is not the same as column major. Also, what are the I/O characteristics of my code? Parallel I/O, that's a very, very useful thing to have. I would like to know what is the write bandwidth or the read bandwidth of any file in my code. Usually reading and writing that file system is the slowest thing you can do. MPI/I/O, is completely supported. And collective operations. If you want your code to scale, don't use collectives. That's pretty much all it is. Unfortunately, we have to use collectives. That's the nature of life. So I would like to get the time spent in collectives as low as possible. Tau has a special context event window specifically for looking at these collective operations so that you can try to reduce time spent there, or at least understand why the time is being spent there. They tend to be very expensive. 3D visualization. This is cool. 3D visualization sounds like a gimmick, but this is probably the most useful thing that I find in Tau. You can draw these 3D charts where the vertical axis is some metric, in this case it's time, and the two horizontal axes here are the ranks or threads or processing elements of some kind in your code versus the code regions. The reason this is useful is I can see at a glance, looking at this 3D model, if there are any patterns in the performance data. you can see right away that there is this inverse relationship between this routine up front that looks like two hills and the thing in the back that looks a bit like a bridge. So there's some relationship between these two routines. That might be something I can optimize. Maybe the routine in the front is spending a lot of time because the routine in the back is not well load balanced. All of this is still profile information, right? This is kilobytes or megabytes. I'm not even looking at the terabytes of trace data. You can actually derive an enormous amount of useful information from just a small amount of data when you view it using the right analysis tools. Also, because we track when messages are sent or received, we can build communication matrices. If we do a 3D view of the communication matrix, looks a little bit like this. We can do topology visualization. This is really fun. I ran a CFD code on a Cray computer a while back, and I did a topology visualization. And I was able to find that there was one rack of the Cray where anything there was a little bit slower, just a little bit slower. And you can actually, then you write the sysadmin and say, hey, look, there might be a heat issue or something here, because it doesn't matter what I run there, it's slow. And that can be a relief if you're looking at your code and you're pulling your hair out like everything is balanced, everything looks perfect, and yet these ranks are still slow. Look at the topology, and there might be a physical reason for the slowdown. How does your code scale? As you increase the number of nodes, who is taking the most time? This is a somewhat old chart. This is S3D running on Jaguar, but the point is still relevant. We run S3D on different numbers of processors. That's the horizontal axis. The vertical axis is the percentage of runtime for each code region. So it's 0 through 100%. That's why it's a square. And what I see is that the number of processors, as the number of processors increases, time in MPI wait all begins to dominate the application runtime. Also, time in this thing called write save file. Well, it's pretty easy to conclude that there's some sort of file I/O bottleneck here. We're trying to write this file, and everybody's waiting for the file write to complete before they move on. And that's an enormous amount of lost time, especially when you're running with 12,000 cores. Different charts that show the same thing. Correlation, this is a very powerful feature in Perf Explorer. If you run your code at different core counts and you see that certain core counts perform very poorly, sometimes it's difficult to figure out why that might be. This is an application where the code was doing a two-dimensional Fourier transform, where it would do 1D FFT, then do corner turn or transpose, whatever you want to call it, and then it would do another 1D FFT. And what we saw was that for certain processor counts, we ran well, and for certain counts, we ran very poorly. The vertical axis is runtime. So you can see there's certain counts where the runtime is very low, and then it peaks back up, then it drops back down. So we look at the code, we try to figure out what's going on. Our first suspicion was, maybe the transpose is not optimized for certain core counts. But these guys had worked really hard, and the code looked good. So we did this correlation analysis, and we found that there were actually 3 events that had the same pattern. You can see there's this blue one at the top, and then there's this red one in the middle, and then there's a really light blue one that you probably can't see very well at the bottom. And they all have the same pattern. And what we found was that all 3 of those routines are calling another third routine, or a fourth routine actually, that was provided by a communication library in the system. That was the guy who was not optimized for certain core counts. At that point, there's nothing we can do. Well, the best we can do is file a bug report with the communication layer and say, you guys need to work on your optimization for certain core counts. But the good thing is you can send this chart to your manager and say, stop telling me to improve the code. It's as fast as it's going to get. Finally, when do events occur? Everything I've shown you so far was profile data. It's all profile data. If you need to see the order of events, you're going to need a trace. And these can be really powerful, especially if you want to see how much time is wasted in collective. The default trace viewer that comes with Tau is JumpShot, which is really old, and if you're going to run for more than 1024 cores, it just isn't up to the task. So I strongly suggest using something like Vampire for this. But if you need to use a trace at a low core count, go ahead and use this workflow. You set an environment Tau trace to turn on tracing, and this is going to generate a whole bunch of different files, which you post-process to produce a slog2 file, which you open in JumpShot. Now, I mentioned Tau Commander early on. So just to recap, right? I told you about performance engineering, the idea of targets, applications, measurements, how you can combine these in different ways to answer relevant questions. I showed you tau, which is the tool you use to actually get the data and answer those questions. But using tau and mapping it onto the idea of targets, application, measurements is a bit of an art. And that's why we're developing Tau Commander. So Tau Commander, this week is the alpha release. It's out in the wild. And the whole idea is, instead of when I use a tool like Tau or Vampire or HP Toolkit or whatever, instead of laying out step by step where I'm trying to get to, just tell the tool what it is I'm trying to do up front and let the tool figure out how to get there. So it's kind of like the difference between a GPS versus a map. You can get somewhere by someone saying, well, walk out of your door and turn left, then go 40 paces and turn right. And you can give step-by-step directions that'll get you there. But if any one little thing goes wrong, you're going to get lost. Or your friend can just give you GPS coordinates, you type them into the GPS, and you go right there. And the GPS works out what are the exact steps. Better yet, if there's traffic on the route and you have to change your route, the GPS can fix that for you. So that's what Tau Commander is. It's like a GPS for Tau. You define these target application measurement configurations directly to the tool, and it will pick your Tau makefile, it'll set the environment variables, it will pick the right command line options, it'll run your code for you, it puts the whole thing together. This is what the dashboard looks like. Sorry for the resolution, it's not very good here, but the top box, each one of these tables is actually a listing of objects that are targets, applications, and measurements you can define directly to the tool. At the very bottom, the last table is a set of experiments that I can choose from and to run the code. Another good thing about approaching the tool this way, by giving it the context and saying up front what I'm trying to do rather than just going and doing it, is I can ask the tool for help. If I, for example, tell the tool I want to use direct measurement with probes on an MPI code, and then I go and I give the tool a serial code and ask for samples, the tool can say, hey, whoa, that doesn't make sense. You told me you wanted one thing, but what you're doing doesn't make sense. And if you really want to know what you should do better, you can just ask the tool for help. And it can say, well, here's the difference between direct measurement and indirect measurement, and which do you want to use? This is built into Tau Commander. Another good thing is that if you're approaching if you're coming to a vanilla system, like your laptop, right? You've never installed Tau on your laptop before. Maybe one or two of you have, but probably not. You don't know what configuration options you're going to need to get Tau installed correctly for your code. But if you tell Tau Commander what they are, Tau Commander can take care of that for you. You can also download all the dependencies and install them and configure them as necessary. Score P, all the rest of it, it can take care of this for you. So you don't have to worry about it. And then finally, because you've actually structured your performance engineering workflow and described it to the tool, it can maintain your experiments for you and actually maintain the provenance of your performance data. Every time you run the code, every time you execute your application, it creates a new trial of your experiment and records a snapshot of all the environment variables, all the loaded modules, all the system state that might be relevant to the performance of your code. And it records that with the performance data. It co-locates it right there so that you aren't going to lose it. And then you can always go back through the database and figure out what was the performance of my code on this system using this measurement and this configuration exactly and on what date. Who ran the thing? And another good thing about this is if you ever change your configuration, say you are switching through different applications or different measurements, Tau Commander will go and reconfigure the system for you. It'll take care of the nasty details of picking which MPI libraries you should link against in Tau. Tau configuration lines can be like, like many hundreds of characters long. They can be quite hairy, so it's nice to use Tau Commander to sort that out for you if your application changes. But the workflow won't change. If you use Tau Commander to manage everything, just keep using the same workflow, change your target or application or measurement, and the tool will react to those changes to make sure that your code is built in the right way. I have some case studies that demonstrate the value of using Tau and how you can get really good performance out of code, but I said something about that at the start of it. So I just want to point out one thing that we did, which was here at Argonne, where we had this code IRMHD, and we worked with a team from University of New Hampshire, ALCS, of course, and University of Oregon. And the results here actually made the cover of this HPC Source magazine because they were really, really good. We were able to take a look at the communication pattern of the IRMHD code, and we found this strong correlation between MPI barrier and MPI send in the 3D view. On the BlueJeanQ, we went and did some optimizations. We changed the communication substrate a little bit, and we were able to get about a 7x improvement out of runtime on this code, which is enormous, right? This is on par with changing the method entirely, which is usually how you get good performance. You do something differently. Using the same method, same result, just 7 times faster. Going forward to BlueJeanQ, we found that by oversubscribing ranks, again, looking at the performance data, we were able to get another approximately 30% off of that 7x improvement. So we were able to get extreme scaling speed up out of this code on Mira based on the tools I've shown you. So I just want to conclude by giving you the link to download Tau. If you want to try Tau, the Tau Performance System, which is the low-level underlying, very powerful toolkit, it's at tauuoregon.edu. If you want to try Tau Commander, which is the high-level workflow management tool, which is alpha release, I can't stress that enough. You do need to be willing to work with me a little bit on this. You can find it on GitHub at this link. At that, I'll just take any questions. Thank you very much.
In other words, does this complement or does this replace a specialized profiler like NVIDIA Visual Profiler?
It has a lot of overlap with something like NVIDIA Visual Profiler. So I use VTune, the Visual Profiler, Vampire. I use several performance analysis tools in a typical workflow. So I can't say it replaces it, but they have slightly different data you're going to get. Tau is going to give you a little more, a slightly more complete picture. It's also going to give you an unbiased picture because it's not a vendor tool. So there is some value there. But NVIDIA, you know, they work very hard on making their profiler a very good thing. So you're going to get a different view of the data from that tool that might include performance effects which aren't visible to Tau. I would suggest you use both, depending on what it is you're trying to do.
Thank you.
Yes.
Sorry, I could not understand that 3D topology properly, but was it the underlying physical topology or the logical topology like MPI Cartesian topology?
I'm sorry, I don't understand the question.
There was a 3D topology map which you had shown.
Oh, yes, topology. Gotcha.
So was it the underlying physical topology, the actual physical topology, or the or a logical topology like MPI Cartesian topology?
That's a good question. So this particular one is the physical topology of a BlueJeanQ. You can also choose a logical topology. If you have a torus, logical torus, you can map it onto a logical torus. There's different ways to view the topology. This particular one is physical, but you can look at the logical as well.
And the previous one which you had shown, which was?
The cube. I think the cube is logical.
Spheres.
Let me see. This guy, right? I can't see because it would be down in the scroll here, but that looks like a logical topology to me. I don't see how this could be a physical one.